All right, so we're recording Math 136 on Thursday, September the 2nd, and my drawing tablet isn't working, so we're starting out in Desmos for as long as we can. And we're looking right this minute at irrational functions. We've just talked about polynomials, continuous everywhere. Here's a rational function, quadratic function in the numerator, linear function in the denominator. And what's the result of taking that ratio? Well, it's the red function here. And think about drawing this. If you had your pencil and you were going to draw or trace this, you'd be coming over and then you're going to zoom way up, but you're going to rezoom clear down here. Now, how do you get from way up here to way down here? You got to lift up your pencil, right? And kind of start over again. At x equals 5, this function's not continuous. In fact, it's not defined at x equals 5. The function is just not defined at x equals 5. Other than zeros of the denominator, rational functions are continuous everywhere. And rational functions get used quite a bit. We use a lot of rational functions. Now, the next class of functions that we want to look at and play with are called exponential functions. And I don't know what to do other than to try this again. I didn't do a thing to this. I didn't change anything. Maybe I need to reinstall some software, and I can't do that while we're in class.
Since most of us are here, did you want to try to restart your computer now?
Yeah, let me do that. So that's a good suggestion, Emily. To restart my computer, I have to end the Zoom session. So you know how long it takes to boot a computer. I'm going to end the Zoom session, but I'll be back just as soon as I get the computer running again. So let me first end, don't go away. Well, you can go get coffee, but other than that, don't go away.
So to continue our talk, we want to talk now about exponential functions. Exponential functions, and this is September the 2nd. So the prototype exponential function might look like y equals a b to the x. And the thing that makes this an exponential function is that my independent variable x appears as an exponent. In a polynomial, the independent variable is raised to various powers, like that for a quadratic equation, which is a polynomial. But for an exponential, the x is in the exponent. Now, what kind of things grow exponentially? Exponential growth is pretty fast, and so it's a very important class of functions. And things that grow exponentially are typically populations or money at compound, interest rates, or one of my favorites is radioactive decay. Now, this is really an exponential decrease, radioactive decay, whereas population generally is growing positive. It's an increase. Money at compound interest is generally positive. It's an increase. Radioactive decay is a exponential decrease. Nonetheless, they're all exponential models, and the canonical form is y equals a b to the x. So let's take an example. Without any kind of compounding, that is, just simple interest on money that you put at deposit, let's suppose that your principal is maybe $4,000. And let's suppose that you get 1.6% simple interest, and that you leave your money on deposit for 7 years. Sometimes that's called the term of your investment, 7 years. Well, what you would be making for putting your money out, money makes money, right? Money makes money for you. Every year you would get 4,000 is what you've got invested, and then you would multiply that by 0.16, and that would tell you how much interest you'd earned that year. And it's a 7-year term, so you'd multiply that by 7, and that's what you'd be given for the use of your money at the end of 7 years. And of course you'd also get your 4,000 back. So this is at simple interest. There's no compounding going on at all. But it seems like a better, and maybe we could argue a fairer situation, would be each year you earn this amount. Why let the people that borrowed your money keep this interest without paying you anything for using this interest money? If at the end of the first year they would add this amount, not the 7, but the number in parentheses, if they would add that, that's your annual earning, to the 4,000, and the next year they would pay you for borrowing from you 4,000 plus this amount, and the next year they would calculate, it'd be bigger than this, because you wouldn't have on deposit $4,000, you would have the sum of these two. And so if we would compound the interest, that is, take the interest earned, add it back, and it becomes principal, if we would do that annually, we would earn more money than if we just leave the 4,000 alone, and then at the end of the term they give you the amount of interest you earned. Well, if they are adding the interest on a regular basis, that's called compound interest. And the formula for the compound interest, if I let P be the principal, how much money you control or they owe you at the end of T years, P of T is equal to the initial principal, P0, how much you loan them, times 1 plus R over N to the N T, where T is the variable, the independent variable that you see right here, because this formula will tell you at 2 years or 2.5 years or 3 years or 5 years what your holdings are. So P naught is what you started out with. R is this simple interest rate that we agreed to. N is the number of times per year that we're going to compound your money. Now it could be 1 or it could be more than 1. It could be monthly, in which case N would be 12. And NT, the product, is the exponent now, and NT would be the number of compounding periods. And so if we are interested in the amount of money that we would have earned at the end of 5 years, then our formula would look like this. It would be 4,000 and then 1 plus, and 0.16 is the interest rate. And let's suppose that we've got monthly compounding. Then our compounds per year would be 12 if it's monthly, and that would be raised to the power n 12 times the independent variable t that we're playing with times 5. And this 12 times 5, that would be 60 compounding periods. And the 0.016 divided by 12, that would be the interest rate per compounding period. You do it 12 times a year, so you don't get all of this each compounding period, you just get a 1/12 of it. All right, and if anyone's interested, we can get a calculator and pretty easily find out what that amounts to, and I will do it just because it's fun. 4,000, and then that would be times 1 plus 0.016 divided by 12, and then raise that to the power. 12 times 5 would just be 60, and at the end of 5 years, my money would be worth 4,332.92 to round it to the penny. Now, this problem wasn't really about figuring out how much your $4,000 investment was going to be. It was about illustrating the use of exponential growth. And this is an exponential formula. How do I know that? The independent variable is t, and t appears here in the numerator. Now, another form of this same idea. In this example, we've agreed to do the compounding, that is to add the interest to the principal 12 times a year. So maybe you are Bank A and you're compounding 12 times a year, and I'm Bank B, and to be competitive, I'm going to say, you know what, I could compound every week instead of every month. And it seems like every week would be better than every month. So I'm going to advertise that I'm doing weekly compounding. And if I did that, well, really all that changes is n becomes how many weeks in a year? 52 instead of n equal to 12. And so my formula would change accordingly. Now, as soon as I compound weekly, that Bank A is going to compound daily, and then I'm going to counter by compounding hourly. And you see, to do that, all we're doing is changing the n. But as this n gets bigger and bigger, the time between compoundings gets smaller and smaller until we finally approach something that I would call continuous compounding. And the formula for P of t, if we're doing continuous compounding, is P0 e to the RT, where P0 is the initial investment, R is the same as it was before, it's the simple annual interest rate, T is the number of years, that's the independent variable, and E is this mysterious number that just pops up in so many different applications, but it's about 2.718281828, and it's an irrational number, meaning that it does not have an exact, I'm going to make these tildes, which we use for approximately equal to. E does not have an exact decimal representation. It keeps going on and on forever and ever, and the periods, the digits are going to be different. There's not going to be a pattern in these digits that we can exploit. So it's an irrational number. And I think in the next few hours we'll see where E came from. In fact, you can see right now where E came from. Refer you to your textbook in this section that we're talking about right now, kind of the latter pages of the review text. So if I compound continuously, I would get, after, just to have a different value, say after 6 years, I would have 4,000 e to the 0.016 times, and my t would be times 6, because we're talking about 6 years here. Now, how do you calculate that? Well, your calculator has got an E key on it, and so you would use E. And when I press the E key on my calculator, this is my scratch paper over here. Let me change color so you'll know this is scratch paper. When I press E on my calculator, the display on my calculator gives me something that looks like this, and it's waiting for me to enter the exponent right here. So if I would enter the exponent don't have room to write it there, 0.016 times 6, then the calculator would return e raised to that power. Now let me use my calculator and get the answer to p of 6. So you got to turn the calculator on and say 4,000 times, and find your e key, e to the 0.016 times 6, and say equals, and it's equal to 440303. Actually, it's 04, and not to be a stickler about a penny, I will write 04. And that's how much money you would have after 6 years. All right, so that's just an application, one kind of fairly common application of an exponential function. Let me see what else we want to say about this. It's not always the case. I mean, it's a little bit hard to think about how money is compounded continuously, except through a mathematical formula, because we think of money, if we're compounding it, as being at some point in time we add the interest to your principal. But if I think about a population, then births are adding to the principal, that is, they're adding to the previous population, and that happens all the time. It doesn't happen just on Tuesday morning. That happens every day of the week, every minute of the day. So that would be easier to see as an application of continuous compounding, and actually it follows this formula right here. So right now I'm not going to do an example, but you can think in terms of maybe deer on an island where the deer population is sort of isolated, and maybe the island's out in the middle of the Lake Michigan, and the deer multiply, and we could track how many deer we have with the formula P of T, which would be equal to the initial deer population times e to the reproductive rate of the deer times how many years into the future we're talking about. That is the independent variable t. So another application of exponential function. Now very often, and let's think about deer on an island, very often I might want to know something like this. Suppose we start with 500 deer, but we know that the island will support only 600 deer. So when the population gets around 600, if it does, we're going to have to make a decision. We're going to have to start feeding the deer because the island's not big enough to support them, so we'd have to bring in hay bales or drop them out of an airplane. Or we could start allowing a certain amount of hunting on the island and let hunters cull some of the deer population. Or we could capture the deer and move some of them off the island to keep the population down below 600. Or we could introduce predators like wolves. So, you know, there's lots of management strategies that would be available. But the thing is, we got to start planning. So we want to know, when is that population going to reach 600? When do I have to start taking action? And a quick sketch would be maybe something like this. And this population would start off at 500. That's what we said. And then it's going to grow exponentially. So not linear. It's going to be growing with something that looks like that. And the further out we go, the faster it grows. You see that's getting steeper and steeper and steeper. And there's a point here where we would have a population of 600. And the question I'm asking you right now is, where in time, this is my time axis, where in time is this going to be? I need to know, because if it's going to be next year, I better get on the stick. If it's 10 years out, I've got some time to examine my alternatives. but I need to know what value of t is going to give me a population of 600. When is that population going to reach 600? Now, it's not hard to see that this is our function that tells me the population. So I want to know a population of 600. I want to know when 500 times e. Oh, we've got to make an assumption or a measurement about this reproduction rate. But suppose that that's 2%, so that'd be an O2. We would know that from historical observations of deer populations. All right, so how many deer do I have at time t? I've got 500 e to the 0.02 t. When is that going to be 600 deer? So there's my basic equation, and I need to solve for t. My dilemma is that t is in the exponent. So I want to break t out of that exponent. And to do that, I need logarithms. And so we need to use logs. And logarithms are functions that are the inverses of exponential functions. Logs undo exponential functions. And if you've looked at your calculator recently, you, on most calculators, will find an ln x key and an log x key. And logarithms have bases. So the definition of the logarithm is that the log base b of a number a is equal to x if and only if the base b to the x is equal to a. Logarithms are exponents then. This says the log of a is equal to x, and that means that if I take b, the base, and raise it to the power x, I get a back. The logarithm is an exponent. Now, your calculator has got two buttons, ln x and log x, and generally, though I will warn you, not always, but generally on the calculator, you've got the two buttons. This one is used for log base e. ln x is a log base e of x, and log x is a log base 10 of x. This is called a natural logarithm, and this is called a common logarithm. So we've got natural logs and common logs, and in truth, there's no reason not to have other bases. The bases we want to be not equal to 1, that won't be useful, and we'd want them to be positive. But if we would use, say, 2 for a base, this would be a log base 2. And it's kind of fun to work with log base 2. They're used a lot in computer science, but I can illustrate the definition very nicely with the log base 2 by asking you just to solve in your head, what's log base 2 of 32? What does that equal to? Well, remember, if that's x, then the base 2 to the x has to be equal to 32. And we know 2 to the 5th is equal to 32. Multiply it out on your fingers if you want to. 2 to the 5th is 32, so log base 2 of 32 is equal to 5. Now, read your book and ask me questions, but this definition of the log gives me a property that's very useful for solving this equation about when did the deer population hit 600. And the two things to know would be that a log base b, any base that's an appropriate base, of the base is equal to 1. Because what is the log base b of b? It's the exponent I have to put on b to make b. So log base b of b is just equal to 1. And the second thing that we can observe here would be the log, and it doesn't matter what base we're using, b of a, some value to the x, is equal to x times the log base b of a. This is the property combined with this one that lets me solve an equation like 600 is equal to 500 e to the point 0, 2 t. And it lets me solve it this way. Let's just go through the steps. I'm going to scroll just a little bit. And I want to solve this for t, we know. So the first thing I'm going to do is to just clean it up a little bit. 0 to t by getting the thing that holds my t all by itself on the left. And how did I do that? I divided both sides by 500. So this would then be 600 over 500. And of course these zeros would cancel out, so this would be 6 over 5. Now if I'd used this property right here, and I think I'm going to take the log of both sides. I believe I'm going to use the natural log. So I'd write ln e to the point 0, 2 t. If I take the log of the left side, I've got to take the log of the right side also. What I do on the left, I've got to do on the right. So that's the next thing I'd write. Now I picked the natural logs, and the reason I did that was because, remember, the natural logs are base e logs. So the log, although we don't write it, the base is e. Now this property says that if you're taking the log of an exponent, a number raised to an exponent, then that's equal to the exponent times the log. So writing out those words, this would be O2t natural log of this guy, of e, and that would still be equal to the natural log of 6 over 5. And then we're going to use this property because, remember, this is natural logs. This is log base e of e. So we didn't write the little e down here, but we know it's down there. E to the what is equal to e? Well, e to the 1. So this expression is just a 1. And I knew that was going to happen. That's why I took natural logs. So I'm exploiting that property. And now what I've got is 0 to t is equal to the natural log of 6 by 5, or t is equal to the natural log of 6 by 5, and then that would have to be divided by 0.02, and when I did that, I would get, and nobody knows these by heart, so we use our calculator, I would get the natural log. I use a lot of calculators, and it's different on every calculator. There it is. Then, oops. Excuse me, Mike. Calculator was doing something a little wonky there, so I'm going to just go to a different calculator. The natural log of 6 by 5 divided by 0.02 is 9.12, and this would be years. So using exponential functions and logarithms, we've just made a prediction that our population of deer is going to hit 600 9.12 years after we introduce the deer. So if I'm just introducing the 500 deer today, I've got 9 years before I have to worry about it. But after about 5 years, I better start doing my planning and deciding whether I'm going to buy hay or introduce wolves onto the island. So a lot of study and a lot of work has to be done there. But just using the exponential function and logarithms, that lets me solve a really important class of problems. Now, I think that's everything that we're going to include in this lecture. So let me wrap it up here. I thank you all very much for being here, and office hours on Monday at 10 to 11, and I will see you on Tuesday morning at 8 o'clock. Have a good weekend. Stay safe.